Hi! So, I will be presenting games in biology and how can we apply it in real life and also in biology. So, come on in! What is game theory? Well, it helps with decision making and it focuses more on the study of strategic decision making where there are instances called games and participants called players. This is where we deal with problems in which a player's strategy is depending on other players' choices. Well, we all know that the decisions we make would be beneficial to us. But first, let's move on to the next parts first. Before I start with this presentation, let me ask you a question. Will game theory really help us in our everyday lives? Is it really important? Can we really rely on it? Well, I'm glad to tell you that yes, game theory can have a huge impact in our lives and actually almost every time. Here are some examples of decision making in life. In sports, one decision can have a big impact to the match. For business, what can I possibly create to earn during this ongoing pandemic? Personal decisions, I will not be able to finish my requirements in one day. So how will I be able to manage it? As long as there is decision making, game theory will always be there and it will never leave. Moving on, a game is composed or always composed of players, actions, and payoffs. It basically speaks for itself. The players are the ones who will decide and will be playing the game. The actions are the very move that determines the outcomes of the games, and the payoffs are the outcomes that can come in the form of the games, which is a positive payoff, and losing, which is a negative payoff. Games can be represented by two types, the normal form and the extensive form. The normal form, where there is an arrangement that indicates the player's strategy and its possible outcomes. On the other hand, the extensive form is done with a graphical strategy and its description is done through a decision tree, as you can see on the picture. Let us now proceed to the different types of game theory. First, there is a type of what we call cooperative and non-cooperative game theory. In the cooperative game theory, it is more on teamwork and unity to reach a goal. This type is what we call the Shapley value. The Shapley value is defined as a solution concept that is used in game theory that involves a fair distribution of both gains and costs to several actors working in a coalition. Moving on, the Shapley value also has four axioms. First is the marginal contribution. It is determined by what was gained or lost when they are already not in the game. For the second axiom, interchangeable players that have the same value. Third, dummy players have zero value or are not really that important. And lastly, if the game has parts or cost, it should be equally decomposed across the game. As you can see, here is the equation for the Shapley value. Non-cooperative game theory, on the other hand, focuses more on what the player's strategy and the different moves of the other players to get the maximum payoffs. As I was researching, the best example I have acquired is the prisoner's dilemma. So what is this prisoner's dilemma? It is a paradox in decision analysis in which two individuals acting in their own self-interests do not produce the optimal outcome. As a result, both participants find themselves in a worse state than if they had cooperated with each other in the decision-making process. In the figure above, there are two prisoners who need to spend at least a year inside the prison and were offered an arrangement. If one of the prisoners confess and the other does not, the one who confessed will be released from the jail and the other would stay. If they both confess, they would spend at least 3 years inside the prison. If they don't, they spend a year. What the problem here is that both of the prisoners should have a decision to make because they don't know what the other would possibly do. The first prisoner should decide, and it has to be a good decision because who would love to spend years inside a prison cell, right? With this, Nash equilibrium comes in place. It is a result which are in favor of the player and the best decision of the game without the other prisoner's actions. As we progress, the maximum value is introduced. It is basically the best of the worst from the set. Now let us go back to the example. The Nash equilibrium and the maximum value should be the two prisoners confessing as when you compare it to the worst. You get the worst for not confessing, which is 5 years. There's also a decision where they don't confess. Yes, but this will only last for a year, but each prisoner doesn't know what the other player's next step will be, which you will not be able to trust. Again, this is a non-cooperative game that means that all prisoners' decisions should be sure of what they decide and achieve in the maximum payoffs. There are also other types of game theory. Simultaneous. Players simultaneously make one move. Sequential. One player makes a move after the other player is finished with the move. Perfect information. The player is informed with the opponent's action but need not to know the whole game structure. Imperfect information. The player does not know the whole information of the opponent's moves. Complete information. Game structures and payoffs are known to the players but doesn't know the opponent's move. Incomplete information. The game structure and payoffs is not known to the players. Some interesting facts about game theory. The perfect and complete information, they are not really mutually exclusive. It can be either perfect and complete, perfect and incomplete, or imperfect and complete. I would like to add some more information for us to fully understand game theory and its different types. The zero sum. The net effect after the gain and loss of both sides is equal to zero. For example, any sport with a winner and a loser. Non-zero sum. The sum of the payoffs are non-zero. The best example for this is the prisoner's dilemma. Symmetric. It relies on the strategy and it can change identities without changing any payoffs. For example, team sports like basketball, football, and soccer. Asymmetric. It relies on the player, such as table tennis or karate. Finite or discrete. It focuses on winning the game. Infinite or continuous. It focuses more on the continuing of the game. For example, business. As we move on, how can we possibly apply game theory in biology? The theory of games was erected on the foundation of this concept and immediately attracted the attention of economists, among whose principal concern was the problem of making rational decisions in situations involving competition or conflict. Soon, preoccupation with game theoretic models spread to political scientists, sociologists, and social psychologists, who saw in these models a research tool for investigating behavior motivated partly by conflict, partly by cooperation. Game theory can be applied to these three inside the field of biology: the biological interaction, medicine, and evolutionary game theory. Since biological interactions involve two or more decision makers, such as individuals with strategies, biologists utilize game theory to elucidate evolutionary consequences of interaction, in which the payoff for the individual involved is shown for all possible interactions. In the figure above, the general payoff matrix for the hawk versus dove. The payoffs are for player 1 employing the strategies in the rows against player 2 employing the strategy in the columns. The symbol B represents the benefit of acquiring the resource, and symbol C is the cost of the combative interaction. In the upper left quadrant, an encounter of hawk versus hawk. The payoff to player 1 is one half the benefit minus the cost, and it assumes an equal payoff for both hawks. A hawk is encountering a dove obtains the entirety of the benefit, while the dove receives none, as shown in the upper right and the lower left quadrant respectively. If both players adopt the dove strategy, the mutual payoff is the highest, with both players evenly dividing the benefit without cost of conflict. Shown in B are the values of the benefit and the cost of combat used in simulation for a population of 1,000 individuals. Although highest mutual payoff occur when both players are doves, the dove strategy is not an evolutionary stable strategy. Moving on is for the medicine. Decision analysis is important, in which a physician can identify strategies under conditions of uncertainty in order to produce the right medicine. With this, game theory provides supplementary means to interpret the strategies in instances where the actual outcome will depend on the choices of both the physician and the patient. As you can see in the figure above, the numeric data required to answer this question, these values are associated with estimation errors, and the magnitude of these errors clearly affects one's confidence in the quantitative aspects of the analysis. On the other hand, ignoring these errors does no violence to the qualitative aspects of the analysis, and materially simplifies the overall presentation. Consequently, throughout this discussion, we shall assume that numbers to be exact, in accord with the axioms of decision analysis. Then, any difference in survival, however small, will be considered real. Although we believe our use of technical terms to be conventional, we provide an annotated definition of the more important ones in order to avoid misunderstanding. Lastly, evolutionary game theory. Evolutionary game theory differs from classical game theory, and it focuses more on the dynamics of strategy change. This is influenced by the frequency of the competing strategies in the population. It has helped to explain the basis of altruistic behaviors in Darwinian evolution. It has in turn become of interest to economists, sociologists, anthropologists, and philosophers. As shown in the figure, the model, as evolution itself, deals with a population, Pn. The population will exhibit variation among competing individuals. In the model, this competition is represented by the game. The game tests the strategies of the individuals under the rules of the game. These rules produce different payoffs in units of fitness, the production rate of the offspring. The individuals leave the game pairwise contest with a resulting fitness determined by the contest outcome, represented in a payoff matrix. Based on the resulting fitness, each member of the population undergoes to a replication, or culling determined by the exact mathematics of the replicator dynamics process. This overall process then produces a new generation with the equation P times n plus 1. Each surviving individual has now a new fitness level determined by the game result. And lastly, the new generation then takes the place of the previous one and the cycle repeats. The population mix may converge to an evolutionary stable state that cannot be invaded by any mutant strategy. To conclude, game theory consists a lot and can be applied in our daily lives. Whether we are familiar with it or not, life is the game itself, and we are the players of that game. Our every decision will affect the payoffs that we will have, which is our fate and the decisions. Whether our payoff will be a gain or a loss, it will always boil down to us. So we should play this game seriously, well, with fun also, and enjoy it like it is our last game. Our life is more than a game, so we must make the most of every second we have and make sure that your decision count. In the end, you will have the outcome you ought to have. Again, I am Trevor and I hope you learned something from this presentation. Thank you and God bless.